All right. This will be the second part of the section 9.5 video, and we're about to talk about the ratio test, which is one that you'll be using quite a lot. But before we get there, I want to make sure you understand what the ratio test is doing. So I have four questions here, the multiple part questions. So here's what I want you to do. Give an example of a convergent geometric series, and what is the ratio between consecutive terms? Give an example of a divergent geometric series. What is the ratio between consecutive terms? Give an example of a convergent p-series. And here, the ratio won't always be the same, but give the limit of the ratio between consecutive terms. And do the same thing for a divergent p-series. So hit pause and do this as much as possible. Okay, so I hope you have done that. So for as an example of a convergent geometric series, I could have something like 1/3 plus 1/6 plus 1/12 plus 1 over 24, etc. R is equal to 1/2. And we know for geometric series, figuring out that ratio and figuring out convergence basically are the same issue. For a divergent geometric series, I could have something like two, series, want to add them, 2 plus 6 plus 18 plus 54. Here R is equal to 3 and it diverges. Now, let's give an example of a convergent p-series. So I know it'll converge if p is greater than 1. So suppose I have p equals 3. So that's 1 over 1 to the third plus 1 over 2 to the third plus 1 over 3 to the third, etc. And I might want to figure out what's the limit as n goes to infinity of the ratio between term n plus 1 and term n. This is not geometric, so it's not the same ratio every time, but what's the limit of that? So the n plus 1 term would be 1 over n plus 1 cubed. N term would be 1 over n cubed. Maybe you can see what's going on already, but first I will simplify this fraction to n cubed over n plus 1 cubed. And this is degree 3 over degree 3, and they both begin with n cubed if we expand. So this limit is 1. So in the long run, the ratio between these terms is roughly 1. They are getting smaller at every stage, but they're getting smaller in a way where they're almost the same. Right? Between one term and the next, the ratio is very close to 1. It gets small by just a very minor amount. Now, if we do this with a divergent p-series, suppose I take p equals 1/2, it would be an example of a divergent p-series. Here, the terms do not get small fast enough for us to add them together. So our limit here would be the limit as n goes to infinity of the n plus 1 term over the n term. And again, we can manipulate these fractions, so it's root n over root n plus 1, which is the limit as n goes to infinity of the square root of n over n plus 1. And this thing in the inside is approaching 1, so the whole thing is approaching 1. So this one, even though it diverges, that ratio is still the same. So basically what we're seeing is with p-series, whether it converges or diverges, the ratio between consecutive terms is going to be very close to 1. So with this in mind, let's talk about the ratio test. So let's suppose we have some series with terms called A. We are going to compute rho again being this version of R. It's like a ratio, although it might not be technically a ratio. And here we're going to say it's the limit of the ratio between consecutive terms. So this is like R. If this were geometric, if this were geometric, this fraction would always be the same thing, namely R. Here we're saying maybe that's not always the same thing, but what is the limit of this ratio? So rho is very similar to R, and the convergence is very similar. So if rho is less than 1, then it's like r is less than 1 and we have convergence. If rho is bigger than 1, or possibly infinite, then it's like r being bigger than 1 and it diverges. But if rho is equal to 1, right, that's similar to what we would see in a p-series. And we saw a convergent p-series with rho equals 1, and we saw a divergent p-series where rho equals 1. So the idea is 1 is right on that borderline and it's too close to call. So it's inconclusive. We could probably figure out if the series converges some other way, but the ratio test itself is not giving us a conclusion. So let's try these examples. And for this specific test, the ratio test, do practice formally writing out what is the limit of the ratio between consecutive terms. This is the test that is likely to come up on the free response section because it can be done in a very deliberate way and you can show your steps fairly easily. So hit pause and try these four. Okay, so for this first one, we would have the limit as I goes to infinity of the I plus 1 term, which would be I plus 1 cubed over I plus 1 factorial over the I cubed term. And right away, we know dividing by a fraction is the same as multiplying by its reciprocal. In the future, I'm just going to do that immediately. That is acceptable. You can just say it's the n plus 1 term times the reciprocal of the n term. Now, we want to be on the lookout for cancellation. When you do the ratio test, very often you will find things that cancel. And let's notice these factorials. I factorial means we're multiplying together all of the consecutive positive integers until we get to I. And I plus 1 factorial is the same thing, but it goes one farther. Right? So for a more concrete example, I'm just going to put this on the side. If I had, for example, 6 factorial over 7 factorial, let's just think about what that means. We don't even need to compute these numbers. Almost all of these cancel. 6 times 5 times 4 times 3 times 2 times 1's cancel. And this is equal to 1 over 7. When we take ratios between factorials that are kind of in the same ballpark, a lot of stuff cancels and we usually get a very simple fraction left. So when we cancel those factorials, we would just be left with I plus 1. And then we might notice here we have I plus 1 cubed over I plus 1. So we have I plus 1 squared in the numerator and I cubed in the denominator. Well, degree 2 over degree 3, that ratio in the long run is approximately 0. So what's going on here is the terms in this series, as we go from one to the next, they get smaller by such a profound amount that it's almost like we're multiplying by 0 to get from one to the other. Right? We're not literally multiplying by 0, but they get small really fast. So if rho is less than 1, we have convergence. Let's do the same thing here. Let's make those agree. That should have been k. So I can do the limit as k goes to infinity of the k plus 1 term would look like this. And then we'll just multiply by the reciprocal of the k term. Rather than even writing that intermediate step, we can just go ahead and say it's the k plus 1 term times the reciprocal of the k term, because otherwise we'd be dividing by that fraction. All right, let's look for some cancellation. 3 to the k plus 1 over 3 to the k. Well, that just leaves us 3 in the numerator. We have degree 2 over degree 2. This is 3k squared. This is k squared. So the ratio is 3. So even though this is not technically a geometric series, it is behaving very similar to a geometric series with r equals 3. And if r equals 3, we have divergence. So this one diverges. If we tried to add those together, it would just get infinitely big. All right, same one here. So the k plus 1 term, and let's be really careful about this. It's 2 times the quantity k plus 1, all of that factorial. And 4 to the k plus 1, here is the reciprocal of the k term. Um, Here's what I'm going to do right off the bat. Two things. One is I will notice that the fours mostly cancel, and so there's just one single 4 left in the denominator. And then before I do anything else, I'm just going to write this as 2k plus 2. So again, we have factorials. So this is the first 2k positive integers multiplied together. This is 2k plus 2. So it's actually 2 more. So when we cancel those, we would have 2k plus 1 and 2k plus 2 left. Well, k is going to infinity. So this numerator is growing infinitely big, and we're dividing it by 4. The limit there is infinity. Right? The terms here are getting bigger and bigger and bigger. And maybe that's not obvious when we look at that formula, but the ratio test makes that very clear. So this diverges. And one more. So the limit as n goes to infinity of the n plus 1 term times the reciprocal of the n term. So we would have 5 times 4n minus 1. If we simplify this, we would have 4n plus 4 minus 1, which is 4n plus 3 times 5. Could cancel those 5s if you like. But basically, we have 4n in the top and 4n in the bottom. This ratio is 1. So what that means is the ratio test is inconclusive. If that ratio is 1, the limit of that ratio is 1, then just from that information, we can't give an answer. Now, what I might notice here is I know that in the long run, this minus 1 doesn't really matter, and multiplying by 5/4 doesn't really matter. So I'm just going to point out here what we actually know is that this is like the harmonic series. The minus 1 doesn't really matter, and multiplying by 5/4 doesn't affect convergence, which diverges. So we have other ways of answering the question, but not the ratio test. So the gist of the ratio test, again, is if we have something that is behaving very similar to a geometric series with r less than 1, here we're assuming everything is positive, so I'm not really talking about absolute value, it converges. If it is similar to, right, behaves like a geometric series where r is bigger than 1, it diverges. Here we're just going to use that fact in a slightly different way. So let's imagine this very basic geometric series where we're literally just adding together consecutive powers of r, starting with r to the first. Let's just note that the nth root of the nth term is the ratio r. In this case, the nth term is r to the n, so the nth root of the nth term is simply the ratio. The root test says this is another way of thinking about the ratio. And I'm hiding some details here, but it's basically the same thing. One way of thinking about that ratio r is thinking of it as the nth root of the nth term. So this is called the root test. So for a series, we will compute the limit, because it might not always be the same number, of that nth root of the nth term. And again, we're going to call it rho because it's a proxy for r. in the long run, approximately what do we get when we take the nth root of the nth term? And same thing, rho is behaving very similar to R. If rho is less than 1, we have convergence. If rho is bigger than 1 or infinity, we have divergence. And if rho is equal to 1, it's too close to call, and this particular test will not give us an answer. So just as a very quick example, suppose we have this thing. If you notice you have a power in each term, but it's not literally geometric, the root test could be very helpful. So we could do the limit as m goes to infinity of the mth root of the mth term. Label this rho. For all of these, I probably should label it rho. I'll make more of an emphasis on that for others. Yeah. It's more important when we start applying it to series. So the power and the root cancel, and so rho here is the limit as m goes to infinity of 3m plus 1 over 2m minus 1, which is 3 halves. So this is behaving like a geometric series with r equals 3 halves. So this diverges. And let's just go back so that your notes are better. Let's just fix all of these. Rho equals, rho equals, rho equals, rho equals. Sometimes it's helpful to be able to talk about rho, so labeling is going to be useful for some applications down the road. All right, that is it for this video.